Moving on to the second chapter of the book, and where we'll be talking about the random variables, right? Random variables, and which comes with random distributions. We'll talk about a few classic random distributions, which will help us, analyze things better, right, in a more systematic way. And what we have done so far is that you have some kind of sample space, right? Sample space. You do experiment. You make your observation, right? You toss a coin. You observe what comes on top. Is that head or tail? Maybe you toss two coins, and you observe how many heads. Those kind of things, right? And we have events like you have the sample points here, right? Sample points here, and the random variable. What it does is that it actually is a function. It's a function. Here is a real value. X is real value. Is a real numbers. Real numbers. All right, and the function goes from the sample space to the real numbers. This is what the random variable does. Random variable does. We'll give more examples. And mathematically, the random variables, they are real valued functions from with basically from the sample space, right? So with the domain, when you have a function, you have a domain and a range. With domain being the sample space, and the range is of course the real axis. The real axis, right? Domain range. Okay, domain range. So example. Example, if we toss two coins, right? Toss two coins. And we define, so the random variable is a definition when you do an experiment. We define, right? So we define X, a random variable, a so-called random variable, X. You define it. You define it to be as the number of heads. It's a perfect fine definition, right? Each time you do experiment, you toss two coins, and you observe, and then you write down, right? The two heads I write down 2, the one head I write down 1, the 0 head I write down 0, right? Then you get numbers. When you have numbers, later on we are going to build functions. We can use mathematical tools to study them. Right? So it's always good to have numbers in the functions. What this does is that, well, if I have it maps HH, the sample point HH, to 2, right? To 2. In that sense, the random variable is function. Right? It's in this sense. This is the X random variable. Random variable is a function. It will map xt to 1, right? It will map th to 1. It will map tt to 0. Because it's definition of what do you mean by that random variable, right? So its definition is very important. And we're going to study a few classic random variables And the first thing to keep in mind is this definition. Well, we have a binomial. What do you mean by binomial? We have a geometric. And then what do you mean by geometric? It's the very first thing you need to understand. Right? It's right because of this. If you don't know the definition, then you don't know what it maps a single point to. It's because the definition defines the number of tests, so you map A to 2. Right? And another example, if we have as in the book, there's a picture. If we have a four-sided die, all right. So 1, 2, 3, 4. 1, 2, 3, 4. Right. Here you have 2, 3, 4. So you're going to get like this. Right, like that. Like that. 1, 1, 1, 2, 1, 3, 1, 4, so on and so forth. And 2, 1, 2, 2, 2, 3, 2, 4, right? All those 16 possible outcomes, right? That, if you define the random variable y, it's called a variable, but it's understood as a function, right? Random variable x is y. If I define y to be as we did when we were doing the probability, we will talk about the maximum row. Maximum row. What that does is that it would, you have 1, 2, 3, 4. So 1, 2, 3, 4, right? On the x on the, so it's probably not entirely accurate to put x there. Just say real numbers, right? It's a real axis. So that's real numbers, line. For real number, you use a line to denote it, right? That's pre-calculus, right? Hopefully that's acceptable. You use a real number, a straight line, a line with no limit. It's infinitely extending to both directions to represent all the real numbers, right? Of course, here it only takes values 1, 2, 3, 4, but in general, its range can be the whole real line, any real number, right? It would map, for example, this guy, which will be 3, 3. The maximum row is of course 3, right? 3. So it will map this point to 3. It would map this point 4 to 4. Okay, to 4. Okay. We mentioned the case of discrete. So those are 3 examples. We mentioned the case of discrete. So here we also talk about discrete random variable, which will be the whole focus of this whole chapter 2 of the book, and what we'll be doing next a few weeks, right? So those are the random variables that takes its range, right? That takes finite or countably many values, right? Values, right? Values. For the ones above, for the 2 tosses, for the 2 examples above, the 2 tosses. It's discrete because the possible values are 0, 1, 2, right? 0, 1, 2. For the maximum of the 2 rows, is of course 1, 2, 3, 4, right? 1, 2, 3, 4. So it's also finite. Those are discrete. Okay? And we gave an example of countably many. I don't know if you remember. So if we define another random variable, so we usually use I didn't mention in the beginning. we use capital letters to denote random variables, right? You capital letters. So capital letters for random variables. Capital letters. We X, Y, Z, A, B. A, B usually use sets, but X, Y, Z, W, those things will be our random variables. All right, random variables. So if we define X to be is defined as say for the case we mentioned, you keep tossing until you get the first head. You might get first head right now. Right? You want first toss, get head on first toss, or you might take 2 tosses or 3 tosses. On the very unlucky case, you always get tails. It might happen, right? So the number of defined to be the number of tosses until the first head. Until the first head. In this case, the X takes value 1, right? 2, 3, 4, on and on and on and on, right? So there's countably many. That's also discrete. Which we'll spend quite some time studying this case later. All right. So that's pretty much same old game that we've been playing, right? It's just the only thing on top is, which we said already. We talk about those things. We talk about number of heads. We talk about a probability of event, and then we define something on that event. We now formalize it, saying not only do we have an event, but we define a variable, we define a quantity, right, on that event. And the next concept is the so-called PMF, right? PMF is probability mass function. Probability mass function. All right, probability mass function, which is a function. Is a function. The little p of 1, say maybe 0. Let's start with the example, right? So the 2 toss example, right? For the 2 toss, we are going to define a function which maps the value or number. A function is going from in this case, the function is going from a real number to a real number. The function that I used to. The function above is going from a sample point to a real number. So they're all functions. The domain is different. The domain here are sample points. Over here, the domain is numbers. All right. So we define. I haven't given you the definition yet, but we define this to be. What does 0 map? What does the function map 0 to? It maps to the probability when this random variable that we're talking about now is equal to 0. And the probability of this random variable is equal to 1. The probability of this random variable is equal to 2. Right? That's function. It maps 0 to a number, maps 1 to a number, maps 2 to a number. And we already know. So what's the probability of having 0 head out of 2 tosses? 1 over 4, exactly, right? I see many of you were saying that. 1 over 1/4, 1 over 4, right? So it's HTT. And x equal to 0 corresponds to TT, so it's 1 over 4, right? X equal 1 is 2 over 4, which is 1 over 2. T is 1 over 4. That's a function. That's a so-called PMF, right? PMF. the mass is like a weight. So this probability has a weight 1/4 at 0, a weight, right? If you plot this in terms of this, right? Like this, how do you call this? Like 0, 1, 2, right? You use a line segment to denote the relative size of the value. So it's 1. So here is 1/4. Here is higher 1/4, 1/2, 1/4, right? So that's a mass. The quantity, the amount of stuff on that point, right? The weight. So that's why it's probably a mass function. Does that make sense? If you put stuff along a line, right? If the stuff is discrete, you only have finite number of locations. You put a rock, right? That's a mass. And if it's continuous, like you have a water everywhere, then it's actual distribution. Say you have a molecule is distributed there. Actually, later on we'll talk about probability distribution function, PDF. When there are only finite points, is PMF, right? PMF. So this procedure, I'm using that as an example, but of course we have to abstract it to be able to study the mass behind. So the PMF, the formal definition is that it maps a number, x is number, right? It maps a number, little x. So capital letter is a variable, as I noted above. The lowercase letter, small x, or maybe y's, the small lowercase letters, are numbers. That's the only confusing part for this, confusing point for this part. We're going to use this. Probability of the capital X is equal to little x. That's a mathematical definition. What that means is that, notice that we have parentheses around x is equal to x, which is like x equal to 0, x equal to 1, x equal to 2, right? Think of this example. We have x equal to 0, 1, 2. The little x, the capital X is random variable. It is, once you define it, it stays. That's a function. It's random variable as function, going from sample space to the real line. And the little x is changing. What about 0, 1, 2, or 3, or 4? You can list all of them, but they're all 0 with the rest, right? P of x equal to 19 is 0. Okay? So the probability of occurrence of x equal to 0 means that the probability of the corresponding event. This is the event. This is the event that makes x take the value little x. Does that make sense? As you, as long as you understand that way, it's totally fine, right? So what do you do is that, formally, as outlined in the book, is that if you want to find the PMF, you first list all the possible, as we did above, 0, 1, 2. List all of the possible values the random variable may take. Right? These are all the random variable these are all the values the random variable may take for the number of heads is obviously 0, 1, 2. Right? And for each such value, for each value, there are many values, 0, 1, 2, 3, 4. It can be infinitely many. So when we cannot really list them, we have to use the notation. That's the power of mathematics here, right? We first talk about it. So each value, each such value, you list all of them, no matter how many are there. I list them, and for each of them, I go through them. We went through 0, 1, 2. Once you go through them, for each of them, each value, we're going to denote it denoted by liter x. That's it. Liter x is some number, each of the possible values, right? For each such x, we find the event A to denote A, denoted by A, right? Event, we call it A. A is such that x, the capital X is equal to liter x. E.g., when x is 1 for that when x is 1 for that 2 toss example, for the 2 toss, all right, the A would be the corresponding event, which is HTTH. You go to a number, from a number to an event, and then to a probability. Finally evaluate the probability of A. Which would allow you to define the definition of the PMF. To define the PMF at that point is probability of that event. Okay? So again, in summary, this is a trivial procedure, but because the way it is written might be confusing to some of you, right? This is how it is written. In particular, that 2 equal sign, that throws some people off. But the second equal sign just give you an event. That's the key. Forget about that second equal sign. That's just an event. P of an event. All right? P of an event. So that's why I'm really going slow and trying to emphasize everything here. All right? In summary, we need to find the PMF again, which is like P of x, the little function. Little p of a number x is equal to what? That's a thinking procedure you should go through. P of x is equal to what? So for you to find that out, you go from a number x. You are giving me a number x. I go to an event A. Then I go to the probability P of A. And then we assign liter P of x. Okay, P of x. Questions? That's clear, right? Is it clear? Yeah. Again, we'll be using like x, y to denote the random variables, right? Random variables. And the liter x, liter y to denote the values they take, right? For that reason, well, we had things like x is equal to liter x, right? If you put if you put a curly bracket outside it, remember the curly bracket are for the sets, that make it a set. for example, that's exactly what we did above, right? I'm just repeating. X equal to 1, that's a set. The set of sum of points that makes X 1, right? That's for the two toss example. That's just a set HTTH. The two different ways of representing the same set. If your X is defined to be the number of heads out of two tosses, that's the equivalent. If X is defined differently, of course, they are not equivalent, right? So this, the formally, this is a collection of sample points W such that my X maps W into my little x, which is what we wrote above. The event that make capital X take value of little x, right? The only complication now is that we formally put a curly bracket outside to denote the set. Similarly, we're going to get, okay, if you have y, if you define random variable, if you use capital Y, which I'm used to, use capital Y to denote the random variable. Again, you don't have to use any, the convention is using a capital letter, you can use X, you can use Z, but I'm going to use Y. Then the corresponding number will be little y, right? Little y. Little y. All right, little y. Okay. So we go back to that same simple example. One way to represent the PMF, right? We just list them as we did above. It's y, p of y, or little x, p of x doesn't really matter. Your possible values are 0, 1, 2. Right? You make a table to list them. 0, 1, 2. So number of heads out of two tosses. Right? This is going to be 1 over 4, 1 over 2, 1 over 4. Right? Use a table. If there are not many of them, if there are 1,700, you cannot list all of them. And then what do? You have to give a formula, right? Formula, which is of course always more powerful. You can code it up, put it in a computer, and then later your computer compute it for you, right? Which you can do infinitely long arrays. But here, if you define array, you have to actually hard code it and write them up, right? So P of y for this case, it will be the always out of 4, right? Out of 4, the total number of size of sample space, which is 4, right? So you want P of y again is the probability. You want probability of y heads, right? I mean y 0, 1, 2, 1, 2, 1. What can you use to denote that? To denote you had one variable.
Y plus 1.
So this to choose y, right? To choose y. To choose y. To choose 0, you want y heads. You don't care about where. So out of the two locations, you pick y location. Those locations you're going to get a head. To choose y, which is exactly when y is 0, you get 1. When y is 1, you get 2. When y is 2, you get 1. So to recover that, one formula You give me different y, I get different number, recovers that table. Right? Is that clear? Maybe another example. We are going to form a team of 2 from 3 men and 3 women. All right, 3 men, 3 women. And now we define. So before we talk about probability of some event, probability of having, like for the candidate interview, we talk about probability of having 1 female, right? And that over there we'll talk about probability. So here we actually define random variable. We define the random variable y to be the number of women on the team. Right, number of women on the team. And in this case, again, if we, like y is 0, 1, 2, right? The team of 2, so these are all the possible values. You might have 2 men, you might have 2 women. So it's 0, 1, 2. These are all the possible values. Everything else, you can list them, but the probability gets to be 0, right? So there's no, those are trivial. So the corresponding P of y, all right? P of y, which is the total. So if we don't care about, if we are not in the process yet of figuring out what's y equal to, right? The total number of ways to form this team is what?
6 times 5.
6 choose 2, exactly. Which is 15. 5, right? Is that what you said? 6 choose 2, which is 15. Is 6 times 5, you start with 6, you multiply 2 numbers, divided by 2 factorial, you're going to get 15, right? So we know all these probabilities are out of 15. 15, right? Wait. Right? Out of 15. And you just need to figure out, hey, what is this corresponding event? Right? What's corresponding event? And for the y to be 0, that means the both men, right? The both men. And because we treat everybody, we treat all the individuals differently, right? That's why we did 6 choose 2. So 3 are different. Even though there's 1 case, you don't put that 1, because that different ways to form a team of 2 guys. There's 3 guys to choose from, right? So what is that? 3 choose 2, exactly. 3 choose 2, right? The 3. The 3 guys are A, B, C. Can A, B, B, C, A, C, right? 3 choose 2. Which is, again, we're using A, B, C to denote the guys. We are going to have A, B, B, C, A, C, right? If we want to finish this. Okay? For y to be 1, you want y to be exactly 1, which means there are exactly 1 woman and 1 man, right? 1 woman and one man, because you want y to be 1. If there are 2 women, that would make y 2. So how many cases are there? How many different teams you can form? You have 3 guys, 3 ladies, right? 9 times 3 by 3, right? 3 by 3, 9. Each of the guys can be paired with each of the ladies. So 9. 9. And for 2, you want 2 ladies. That's 3 again, right? So you choose 3. You use D, E, F. There will be D, D, F, E, F for the corresponding event A, right? Oops, there will be 2 different A's. So let's just do event. So here would be like A, D, A, E, A, F, and so on and so forth, right? I'm not going to write down all 9 of them. A, D, A, E, F, B, D, B, E, B, F, C, D, C, E, C, F, right? Yeah. That's right.
Okay.
So I'm going to use boys for A, B, C for boys here, and here D, E, F for girls, yes. So that will be totally acceptable to do it that way because you need to calculate the numbers. If you were to try to come up with a formula, right? Formula which you can, a nice formula. The bottom is 16, 6 choose 2, which is 15, right? What do we have on top to turn 393 into a formula basically? You want Y, the number of girls to be Y, right? You want Y girls. 3 choose Y, exactly. 3 choose Y. So that would make, like, that's all, only partially done because you haven't formed a team yet. Right. You need to form your team. It's 2-step. First, to pick 5 Y girls, and you still need to form the team, which means you need 2 minus Y boys, right? For any Y, 2 minus Y boys out of 3. Then that will generate those numbers. If Y is 1, you're going to get 3 times 3. If Y is 0, you're going to get 1 times 3, and so on and so forth, all right? And you give the positive values of Y, Y0, 1, 2, right? Y0, 1, 2. Questions? The properties. So the properties of PMF, as you probably have thought about it already. So these guys, the P of Y, those are probabilities. So they should always be non-negative, right? We know, because they are probability. The second one, which is very important, is that, and very useful for to finish this table, to check your answer. If you add them up, add all those pieces up, you should get what? 1, right? 1, exactly. You add up all the Y. Because in general, we don't really know what Y is starting and ending, so just put Y there, which this means you sum over all the possible Y, right? Let me put a note there. This is sum over all possible Y. Okay. This is helpful in the sense that if you calculate this table, and you can check your answer by adding them up. If they're not 1, something is wrong, right? Or like sometimes it's complicated to calculate. Like there are 3 probabilities you need to calculate. You can easily calculate 2 of the 3. Then the last one you don't need to. You can be lazy and just use 1, subtract the other 2. It will save you some time. In particular here, the 0 and 2 are easy to do. In the 0 they are very much similar. But the cases, the 1 is super complicated to calculate. then you don't need to calculate that one, right? So it's good to keep in mind. You can check the answer and use that to calculate one out of that many probabilities. Does that make sense? So that's a PMF. And from this point on, maybe today we'll get to talk about two probabilities, two different, two classic. The next it will be three classic of I think four. So next we'll be talking about four. I mean not today, right? Next few lectures, four classic random variables. Four classic random variables. Okay. And we get to two of them. The first one is trivial, so that's why we can get to the number two. The first one is so-called Bernoulli, B-E-R-N-O-U-L-L-I, Bernoulli random variable. What that is that you simply, it's one toss of a coin, right, of a coin. It can be simplified a coin, but in reality, anything that's binary can be thought of as coin tossing. Is it rainy or not rainy? That's like coin tossing, right? So we'll talk about tossing coin, but it's really so much more than coin tossing. Anything binary can be simplified like that. And they don't have to be equally likely. It's a fair coin versus not fair coin, right? Not unbalanced coin. So as long as you have two outcomes, it can be modeled, can be mathematically modeled as coin tossing. Okay, that's why the Bernoulli is simple but it's useful. You one toss, and you define x. This is defined to be equal to 1 or 0, and if you have a head, if you have a tail, right? Again, head tail is just names. It's binary. You can head can be like wind, tail can be loose, head can be rainy, tail can be sunny, right? As long as it's binary, we call them head and tail, right? Or you win, or or a stock market going up, going down, right? As long as it's binary. And the PMF of this guy would be lead x is it takes value 0, 1, right? 0, 1. One gets p. That's up to your situation. If it's a fair coin, they're both 1/2. So p is 1/2. Maybe p is not 1/2, it's 1/3. Then the other one is 2/3. But that up to be 1, right? That up to be 1. The next is what we've spent quite some time on. Is so-called binomial random variable. Binomial random variable, and which leads to a probability distribution, right? This p of y, that's a probability distribution. So when we talk about random variable, we'll also talk about the binomial. It's a binomial probability distribution. One over 4, 1/2, 1/4, that you distribute the total probability 1 into like that, in that sense. Okay. So there's the definition, right? The definition is that we define a so-called binomial experiment, right? Experiment is such that a few characteristics, right? Few characteristics. Number one is that there are. We're going to use the letter n, a number. For the coin tossing, the example I gave you the first class, the 400 n is 400. You toss coin 400 times, right? The n independent trials. You try something n times. There's one key number is n. All right, and the second is that each trial only has two outcomes: is success or failure. Again, this is just relative, right? As long as it's binary, you can call one guy success, the other one failure. It's just a name, right? The essence is binary. It's binary outcome. As long as it's a binary outcome, right? As long as you try the same experiment n times, you fall into like the weather is not a good example. It's different. Suppose the same day across different years, they are roughly the same weather. Then you observe historically, right? You observe, is it rainy or sunny, right? On many days, or for the same day over many years. Okay. Yeah. Number three is that we have another quantity here. So for each trial, the probability of success is some p, little p. Number four, so we have a second quantity which is important here is p. We have n or p. P is again just some probability. Like when it's fair coin, p is 1/2, right? 1/2. And the number four is we define this definition of the random variable. Again, for any random variable, the first thing you need to ask is what's the definition. So that makes number four key. Key is definition. Binomial random variable means that you define it to be the number of successes. This is of course out of all context, out of n trials, right? So those will be like three key things. You have n, you have a p, you have a y, defined to be number of successes. Okay, number of successes. Then we call this experiment, and by extension, this random variable binomial. Then this is the so-called binomial MP. The two key quantities, we put it that after the name, we inside the parentheses, NP, right? This is a binomial MP random variable. Capital M, that's right. Yeah. Binomial MP random variable, binomial MP experiment, and then it's also a probability distribution, right? Probability distribution. It's binomial, so it's called binomial. Okay. Binomial. The example is again that the same old example. You have 400 tosses, and the y to define to be the number of heads, right? you call head a success. The number of successes is the number of heads. And you don't have to call head success, you can call tail success. Again, it's just relative, depending on what you care for that context. Right? So 400 tosses of a fair coin. If you define y to be, you care about number of heads. So the y, I'm going to use this notation to denote follows, right? So the y random variable follows a binomial expansion, a binomial distribution of 400. P is 1/2, right? Binomial 400 1/2. So that will simply finish the condition of this, the whole thing. If I say this binomial 500 1/3, then you know the context. You know what it means. Your binomial 500 1/3 means you do the same thing 500 times. Each time, the success probability is 1/3, and the y is the number of successes. 3 things, right? The moment we write down binomial two numbers, you get the meaning. No. And the immediate next thing is what's a PMF? It's PMF for binomial MP, right? What's a PMF? What's a PMF? Again, so we start by listing numbers, and then try to abstract it into a formula, right? In formula. And this formula, in the end, it might be confusing, but if you understand it, it's not. It's not. Right? So we have the little y, and then we have the probability for that y, right? The PMF maps value to probability, and this y can be 0. So the total of n trials, so y can be, of course, 0, 1, 2, all the way to n, right? N, right? When you want y to be 0, now we're trying to figure out the event, right? The event. So let's do this. The event. And then we have some, probably we don't need a lot of space for probability. All right. So try to make sure we understand this table, and then we can abstract to the formula very quickly. Right. So you want y to be 0, which means you want no success. Again, think of this as boxes, as we will talk about the counting, right? I have m boxes. If I use S to denote success and F to denote failure, here we want number of S to be 0, which means they're all Fs. So I need to put F everywhere, right? So what's the probability for the F1F? Each time, I need to fill in each box. Each box, I have the probability P to put S. The probability of success is P, which means the probability of failure is 1 minus P, exactly. 1 minus P, right? 1 minus P. So I'm the one randomly throwing S or P, S or F into each box. I throw F with probably 1 minus P. Right? 1 minus P. I need to throw F everywhere. And they're all independent. Remember, they're all independent. Well, independent means that probability of A intersection B is the probability A times the probability B, right? So probability for me to put F in the first one and F in the second one is the probability for the F in the first one times the probability of F in the second one, right? So we should multiply all these probabilities together. This is independent means. Each trial, every time you toss coin is not affected by the other tosses. You need to multiply all those 1 minus p's together, which makes, yes, 1 minus p to the n, great. 1 minus p to the n. Now, the second one is that you want y to be 1. Again, that's the tricky part, right? The tricky part is that I only care about the number of success. That's why the definition is important. I only care about the number of success. I don't care about where. I only want one head. I only count. I don't care about is that the location number 1 or location number 400. I don't care. So we need one S, and everybody else is F, right? So it can be S, F, F, all the way F. That's the case S is number 1. Everybody else is F. And it does not have to be number 1 because I don't care about the location. It can be number 2, F, S, F, and or F. Right? And all the way, it can be the very last one, which is F, F, all the way F, and finally one S. By the same notion as we did the first one, each of these guys would get, they are independent. Each of these would get, I need P for S, I need 1 minus P for all the F. So what do I get? I get P times exactly 1 minus n minus 1. That's only for one of them. How many do we have? N. So the probability is N times P times 1 minus P to the n minus 1. Right? To the n minus 1. N times P times 1 minus P to the n minus 1. They all have a meaning. Otherwise, if you don't know the meaning, you'll get confused. Is that P to the minus 1 or 1 minus P to the minus 1? You easily get confused. If you really just try to memorize it. But if you understand, hey, my y is 1, that means I have 1 S. S is P. As success happens with probability P. So it must be P comes with the power 1. Where 1S means we have n minus 1 failures. Right? So 1 minus P comes with P minus 1. 1 minus P comes with n minus 1. Right? So, let me finish this. You're going to have P times 1 minus P to the n minus 1. They all have dot, dot, dot here. Here is also P, 1 minus P to the n minus 1. Right? For 2, so many for me to list. 1 is easy to list. 2 are so many to list, but again, what you see the pattern. We don't care about where. We only care about the number. We need 2 successes, and it can be S, S, and then F everywhere, right? Can be F, S, S, F everywhere. And you think about the probability for each of them, which we now know is what? P squared times 1 minus P to the n minus 2. You get 2 successes and n minus 2 failures. Right? N minus 2 failures. And what's left is try to figure out how many. How many, right? Above is easy. When we see it as n, because S is traveling around from the beginning to the end. Now you have 2 S's play around. use the counting tools and choose to, exactly. The n locations, n boxes. I choose 2 boxes. For those 2, I'm going to put S. So it's n choose 2. Then we're done. Because the little p of y is a PMF. Again, it's so important to remember the definition. The definition, y is the number of successes. So you're going to get p to the y, right? 1 minus p to the n minus y. And then you have n choose y. And again, this is a complicated formula, but each part has a meaning. If you know the meaning of each part, you'll never get confused. In particular, this part is the probability of having y successes. If you have y success, you have n minus y failures, right? So that's the probability of having m minus y failures, right? And when each of them has you multiply them together, that's the probability of that single event. And here, that is the number of cases where we can have y successes out of n trials. All right?